Right, this is going to be the first of the two videos dealing with the harmonic oscillator. The harmonic oscillator is next on our tour of model systems. As the word oscillator might suggest, this one we're going to use for vibrational motion in molecules. Right? And so if you want to think about the vibration, say of a diatomic molecule, picture the bond. I have my equilibrium bond length, and the bond will stretch and then compress as the atoms vibrate. Okay, that's a very exaggerated amplitude of motion there that my fingers are doing, but that's the idea of this, this vibrational motion, right? If I wanted to do this, picture this classically, there are a couple ways to realize this. One is to take a mass and just attach it to a wall by a spring. So in the top picture there, I have the wall, and then I have my mass would be vibrating relative to that, right? In that case, there, if that's the position where the spring is neither relaxed nor stretched, say, we might call that zero. We might actually want the string to be stretched at the point we call zero, but that's a choice we could make as we set up the problem. That is one way to realize this. The other way to view this is to have two masses attached by a spring. Okay, this is the way we usually think about molecules because after all, we have two masses in a diatomic molecule, right? The bond itself, the electrons in the bond constitute the spring. The good news is that a molecule, therefore, is very much like the way a physicist envisions this, this problem, which is you have the mass in the two atoms, and a physicist would generally want to describe the spring there as massless, right? Because the atoms are very heavy compared to the electrons that are in the space between them. The nuclei are where all the mass is, right? So a molecule is actually a very good approximation of that two masses joined by a massless spring sort of model. Our harmonic oscillator, because it's harmonic, should obey Hooke's law, right? Meaning the force is equal to minus kx, where k is a force constant. That force constant, if we were talking about an actual spring, would have to do with the stiffness of the spring. Right? If I got a tighter spring, I would get a larger force constant. It would be more difficult to stretch it. In the case of a molecule, the force constant is going to be related to the bond strength, right? Because the stronger the bond is, the harder it's going to be to stretch those atoms apart and to elongate that bond. And so that's how to think about what that force constant is telling us. My classical harmonic oscillator should obey Newton's laws of motion, of course, and if we do that, we can put together the equation of motion, which would just look like this, right? This is something that is worked through in any sort of reasonable mechanics class when you talk about simple harmonic motion. A general solution to that equation of motion is written down below there, where it's got a sine component and a cosine component, at least in principle. This introduces omega, where omega is what is referred to as an angular frequency. For harmonic oscillator, this is one of the go-to equations. Omega is equal to the square root of k over m. Right? So the vibrational frequency is going to depend on the force constant and on the mass of the picture, the mass attached to a wall model. Then I want the mass of the atom to be the mass that's in there. Right. That omega is going to be in radians per second. We will often, sometimes we'll work in omega, often we will work in a more ordinary frequency where those are just going to be related by a factor of 2 pi. Right? Because I get 2 pi radians per vibrational cycle. And so we'll be able to interconvert between omega and what we will often label as nu, which would be the vibrational frequency or the frequency of light that we would see the molecule absorb to excite the vibrational motion. If I take my choice of coordinates, I said I actually alluded to this on the first slide. If I put the zero of x coordinate at a point where the spring is stretched out to its maximum extension, then at that point the mass is stationary, right? So picture the case where I just have one mass attached to a wall, right? If I pull the mass out to the furthest it's going to get, and I call that x-coordinate 0, right? At that point, the mass is not moving, because every time it comes back there, it starts going this way, and it's got to turn around and go back the other way, right? So as it turns direction, it's got to pass through a moment where it's stationary, right? And so if I do that, I can put this initial condition on there that says I want time equals 0 to be when the mass is fully stretched out. And that lets me lose the sine term rather, and keep the cosine term. From there, I can say that the position, the x coordinate at any time t, is just going to be given by this form down here, right? And so it's the declaration of that initial condition is what makes the sine go away and the cosine survive from there, right? And again, that's got the angular frequency omega in it, and that gets us our equation for the position of the mass as a function of time. We are very often going to work with molecules. That's our point in doing this. And so in the case that I am working with two atoms joined by a spring, instead of using the mass of one or both atoms, it turns out what I need to do is use something called the reduced mass. We have not met this before. We will use this idea both in vibrational and in rotational motion when we take up the rigid rotor model. The argument for this is essentially saying we want to think about the problem really in a center of mass reference frame, a coordinate system. Right? The reason for that is we want to separate vibrational motion from translational motion. Translational motion is the movement of the entire molecule. Right? So any motion that moves the center of mass of the molecule is part of translation. And we'll actually use at times the particle in a box model as our model system to describe translational motion. When I talk about vibrational motion, I want to picture the molecule stretching in such a way that its center of mass does not move. Okay, so the motion is all about the vibration and not about the molecule just flying through space. All right. In order to do that, that's why if we were in a center of mass coordinate system, that would happen naturally, right? The easy way to do this is to replace the mass with what is known as the reduced mass. The reduced mass gets this symbol here as mu, and the easy way to calculate mu is just like this. It's the product of the two masses over the sum of the two masses. Right? Note that the reduced mass is still going to have mass units because it's got mass squared on top and mass on the bottom, so it does still have mass units. It is, if I had a homonuclear diatomic where the two masses were the same, when I do my masses, I'd get what? I'd get m squared on the top and I'd get 2m on the bottom. So in that case, for a homonuclear diatomic, the reduced mass is going to be 1/2 the mass of one of the atoms, right? So very different from the mass of the entire molecule. Right? There is also a more elaborate formula that you can put together, which involves actually finding the center of mass of the molecule and things. There's no reason to go about it that way. This relatively simple equation works just fine. So we want to be in the habit of using that when we're talking about vibrational or rotational motion, because we need that center of mass reference point for both of those. Oops. I'm going to just we'll do a quick calculation here to illustrate a couple of ideas about the reduced mass. Okay, I'm going to find the reduced masses for HCl and for DCl. HCl just hydrogen chloride, DCl hydrogen chloride, but where we've replaced the hydrogen atom with deuterium. The deuterium is an isotope of hydrogen that has a neutron in it. Right, so the mass, the atomic weight of deuterium is roughly 2 AMU versus 1 AMU for the HCl. My general equation for doing this is that mu, the reduced mass, remember, is m1, m2 over m1 plus m2. If you have a habit of losing track of equations, if you ever have a hard time remembering which one goes on top, if you do that upside down, then you get 1 over mass instead of mass for units, right? And so I kind of rely on that to make sure I'm doing the equation in the right place when I start out. So first I'm going to just calculate the two things. I'm going to do them in AMUs just because it's easier that way. So for my HCl, I'm going to say mu is equal to, I'm going to use 1 for the mass of the hydrogen. I'm going to use 35.5 for the mass of the chlorine. And then I'm going to say on the bottom, I get 1 plus 35.5. That gives me 35.5 over 36.5, which would be 0.97, according to my notes. If I do DCl, I'm going to get mu equal to 2 for the D. 35.5 again is what I'm using for the, sorry, I got a bad spot there. 35.5 for the chlorine, and on the bottom I'm going to have 2 plus 35.5. That one's going to be equal to 71 over 37.5, which is equal to about 1.89. If I look at those, I can see that the two reduced masses are actually very close to the masses of H and of D, right? The reason for that is that HCl, because the chlorine is very much heavier than the hydrogen, right? If this is the chlorine, it's the big mass, the hydrogen has a much smaller mass. That means the center of mass of this molecule is pretty much right where the chlorine is, right? Because almost all the mass is there. That means when it vibrates, the chlorine doesn't move around much and the hydrogen moves around a lot, right? So the chlorine stays fixed and the hydrogen oscillates relative to it. This case is actually relatively close to the idea of having the one moving mass attached to an immovable wall, right? Because the chlorine is not really going anyplace. If I had, instead of doing that, changed the, and these would both be in AMUs. I didn't write units there, but I really should. Okay. If I were to do, suppose I had changed the chlorine isotope instead of the hydrogen isotope, right? If I did H with chlorine 35, I have notes over here that tell me for that one, I would get 0.972. I swear I wrote numbers there, really I did. And if I did H with chlorine 37, which is the other stable isotope of chlorine, then I would get 0.949. Right. In that case, note that not much happened, right? My reduced mass stayed very close to the same. That's because, again, the center of mass is pretty much the chlorine and the hydrogen is doing all the moving, right? And changing the chlorine isotope doesn't have very much effect on that. Okay, so changing H to D has a big effect because that's actually doubling the mass, whereas changing 35 to 37 is only changing it by a few %. Right, and so if we're trying to actually shift the masses, there's certain isotopes that are more sensible to try changing than others, and sometimes we do spectroscopy. We actually do take advantage of that, and maybe swap out an H for a D someplace in a molecule and use it to identify which peaks belong to which vibrational motions, things like that. We'll talk about that a little bit when we take up spectroscopy in the next module after this one. We want to set up a quantum mechanical version of the harmonic oscillator, right? And to do that, we need a potential energy function because that has to get built into our Hamiltonian, right? We can find that by starting off with an equation for the change in potential energy as the spring stretches and compresses, and that should be as written there. If we integrate that, we get this piece down here, which just says V is the potential energy, right? That's my potential. And the potential energy is just equal to 1/2 kx squared, all right? The integration constant C over there, it's relatively simple to break things up so that we can force that to 0, okay? And so we're going to use 1/2 kx squared as the potential energy function when we build our Hamiltonian. All right. The kinetic energy part of the Hamiltonian we already know. We know that from everything else we've done, right? That's the piece with the second derivative multiplied by a couple of constants in front of that. So we take those and now we've got our Hamiltonian, right? This is my Hamiltonian. The first term here, that's the kinetic energy. This piece, that's my 1/2 kx squared, right? And that multiplies the wave function. When I do that, I get E over here, and that E should be the eigenvalue that's going to tell me the energy of the state for that particular wave function, all right? The solutions to this particular differential equation will again contain a quantum number. If your a bit more seriously into differential equations, you may recognize the fact that the solutions to this particular one involve something known as the Hermite polynomials. Okay, if you're not, or if you've forgotten enough math to not have that mean anything to you, that's okay too. What I've done is I've written down here the first couple of wave functions for the first couple values of n. Right, the quantum number in this case, for now, I'm labeling as n. In the future, we will probably shift to labeling this one with a v because it's the vibrational quantum number. That's mainly just to avoid calling all the quantum numbers n, because that, as you might imagine, would get pretty confusing fairly quickly. Unlike the quantum number from the particle in a box, this one is allowed to be 0, right? So there is a 0 value for this vibrational quantum number, okay? 0 is the lowest energy state, then it goes up in whole numbers from there, right? And I've written down just 2 of the functions there. In the way the equations are written here, for simplicity, they include a term alpha, and this alpha has this value here, right? It's the square root of k mu over h bar, where k again is the force constant, mu is the reduced mass. Right, so in the various places where there's alphas, we could stick that in there. It makes the equations a little bit more garbledy looking, and so I thought it was simpler to put them in that that somewhat reduced form. Right, the textbook I think does include equations for a couple of more wave functions above that, but these will serve us nice enough for now. Next up, now that we have wave functions, we want to find energies, right? And so if I want to find the energies, what I have to do is I'm going to take this wave function, right? This is the psi 0 wave function, and it's got some converting done, right? So this uses the fact that k is equal to m omega squared, and so where the m omega squared is up there, that was a k before, right? Because k is equal to m omega squared. That's because what omega is equal to square root of k over m. And that gets us that. So if you're trying to get from the equation we left behind over here to which does not have the omega term in it, right, to there, that's the manipulation that was involved. The general form of this equation looks like this, right? It's got constants in front of the exponential, and then it's got e to the minus some other constants times x squared. Right. So the second derivative, if I take the second derivative from this function here, doing it that way makes it relatively easier to confirm that this should be what the second derivative looks like, okay? For our particular case here, these are what we've got for the A and B, because those are the clusters of constants, right? So that m omega over pi h bar all to the quarter power, that's the piece in front of my exponential, so that's A. M omega over 2h bar, that's the stuff that's multiplying minus x squared in the exponential, so that's b, right? If I take that, I can then write out what my derivative is, right? And let me just do that. My derivative is, I'm going to do this, this is second derivative of the 0 wave function, okay? And that's equal to 2 times m omega over 2 8 over pi, sorry, I got ahead of myself, pi h bar, all of that to the 1/4 power. The next one is what I started to write, m omega over 2h bar. Okay, that's my my 2AB, the piece in front. So that's this piece. Then I've got the next one, which let's do it this way. This is 2. I've got m omega over 2h bar. I've got x squared minus 1. Then I've got e to the minus m omega x squared over 2h bar. All right, if I look at that, I can see that this is the exponential that was originally in the wave function, right? And down here, this piece is my a, which is the constants that were originally in front of the wave function. So those two pieces that I just underlined, if I break those off of there, those are psi, right? And so that means I'm going to rewrite this by saying that my second derivative gives me 2 times m omega over 2h bar. Then I've still got the piece in the square brackets, 2 times m omega over 2h bar x squared minus 1. I've got all of that times my wave function psi back again. Okay, so that is my second derivative. I could, if I cared to, I could clean that up a little, because I could take out that 2 and that 2, and I guess that 2 and that 2 could go as well. All right, so that gives me my, my second derivative. It does also confirm that when we take the second derivative, we get something that still has the wave function in there. So we're headed towards being able to establish that we're going to get an eigenvalue from that. Okay, so that's my second derivative piece. Now I'm going to take that and I'm going to just flip back for a second to remind us that that corresponds to this. So that piece is going to get multiplied by minus h bar squared over 2m. Then I'm going to also have to do the 1/2 kx squared times psi to get my whole Hamiltonian in there, my whole Schrödinger equation. Okay, and so when I do that, let's come down here and say what I want altogether is I want minus h bar squared over 2m, second derivative, where we know the second derivative piece now, plus the piece that when I wrote this up before, I had this as m omega squared x squared over 2 all times psi 0. Okay, and all that is supposed to be what I'll call E0 psi 0, where the 0 is just labeling that this is all for the state that has quantum number value of 0. Okay, now we're going to put in what we just got for the derivative. Okay, so we'll put minus h bar squared over 2m here. Okay, then we've got an m omega over h bar. Then we've got the part in when I wrote a square bracket before, so I'll do it that way again, I think, which gives me an m omega over h bar x squared. I've got that times x squared. And I've got a minus 1. I've got all of that times psi 0, right? Then I've got over here, I've got my m omega squared x squared over 2 all times psi 0, and that's supposed to be equal to E0 psi 0. Okay, let's try and do some cleaning up of things here. Okay, if I rearrange that and cluster up some terms, my notes tell me that I can do the following. So let's see what we're going to do. There's a lot of things going on here. Let's just do some of it here. Here's an m. And there's an m, so let's cancel those, right? Here's an h bar, and there's an h bar squared, so we can cancel the squared part of that, right? So this gives me minus h bar omega over 2. And then this piece is still the same, my m omega over h bar x squared minus 1, still multiplying psi 0. And then I've still got the same combination of things here. M omega squared x squared over 2 psi 0. So that's all equal to E psi. Okay, and if we do the final little bit of cleaning up here, this says that I get what? I get minus m omega squared x squared over 2 plus h bar omega over 2. I get all of that, psi 0. I don't know why my psi's keep trying to come out that way, plus the same piece here, omega squared x squared over 2 psi 0. Really, I promise I'm making psi's and not t's. And this term here and this term there are the same, so those two cancel. And that leaves me with the energy E0. When I'm all done with all that work, I get that E0 is equal to h bar omega over 2. All right, so after a great deal of drudgery work there, we get a relatively simple expression for the energy, which says the ground state energy is just h bar omega over 2, right? Which is a nice simple result, even if getting there is not really all that simple, right? We could do the same for the n equals 1 state. And if we do that, I will say the beginning of it looks like this. It says that I would again go through and do the second derivative, starting with those in recognition of how much time I just spent there staring at the iPad and writing on it, and the fact that I already put the equations for this in the stuff that I posted to you. I think maybe I'm going to cut to the result of this one rather than stretch this out and do all the writing through again. But if we do that, I will say that after a bunch of work for this, what we get is that, I thought I had fixed that problem. We get that E1 is actually equal to 3/2 h bar omega, right? And in fact, if we do this and keep going through higher and higher wave functions, we will find that they keep going up by an increment of h bar omega. And so our overall expression for the energies is going to turn out to be that the energy of state n is equal to n plus 1/2 h bar omega, and that's a nice and simple equation for us, okay? But I hope that you don't mind if I don't do the writing out of that, but it's a bit of a struggle the way I'm doing this, and I think you'll get at least as much benefit by just looking through the equations as by watching me attempt to scribble them out here. So if you'd rather see more of the writing, let me know that, and I can try and adjust how I do future ones of these. So if I take this and sort of summarize what we get out of these things, this has the wave functions and the probability densities for the first 4 energy levels of the harmonic oscillator, right? And then over there on the side, I've got an equation. This just says that my energies are always n plus 1/2 times h bar omega, right? That's the general expression for the energy of a state. You'll notice that in the picture, wherever I stole this figure from, it's using a v for this quantum number over here, right? And I kind of hinted to the fact that we'll do that later. We used an n, at least for today, right? In these figures, you'll also notice that the wave functions are drawn superimposed on that parabola, right? The parabola is what would be the classical limits of motion, right? So if I actually had the 2 balls joined by a spring, right? However far I stretch them out, the stretching out part, if I put more energy in, I can stretch them out farther, right? And as I climb up in that parabola, those walls of the parabola represent what are called the classical turning points, the points at which the mass would stop, turn around, and go back the other way. Right? So if I was at an energy that corresponded to this level up here, I would be stretching with that being the shortest distance and that being the longest distance that the 2 masses got apart, right? That's what the parabola is there for. Notice that the energy levels here are evenly spaced, right? Because every time I go from one up to the next, my energy goes up by h bar omega or by h nu, right? Here they're labeled as 1/2 h nu, 3/2 h nu, and so on, because h nu is equal to h bar omega. And so we can use either one of those 2 ways of expressing the frequency that we like. Notice that there is a non-zero 0-point energy, right? So the minimum energy is h nu over 2, or h bar omega over 2. That says we can never actually stop the vibrational motion, right? So if I had a sample of molecules and I even could cool them to 0 Kelvin, in principle there is still vibrational motion because there is this 0-point energy that persists, right? As always, the probability densities come from taking the wave function and squaring it, right? And so the right-hand set of figures over here corresponds to those probability densities, right? And you can see they get a little bit less symmetric looking as we go up through those wave functions. But we'll talk in the next video a little bit about what happens in the limit of going to very high energies or very low energies, things like that from here. But for now, what we've done is we've established what the wave functions look like and what the energies are for the allowed states of the harmonic oscillators. Once again, we've got a quantized system, right? Certain energies are allowed. Those allowed energies are each characterized by a quantum number, a value of the number that we're somewhat alternately here labeling as either n or v. And I apologize for not being 100% consistent on that. It kind of depends on the context in which we talk about this, which symbol people generally use for that, okay? Also, be a little bit aware of, right now we've got things in front of us that have V's over here and they've got Nu's over there, right? So be on your toes for V versus Nu, frequency versus a quantum number to make sure you don't cross those up, okay? All right, the next video will also deal with the harmonic oscillator. It will take up a little bit of comparing the classical and quantum oscillators, and then it will talk a little bit about vibrational spectroscopy.